Welcome back, guys. In this video we do several more examples of writing integrals in polar coordinates, including some examples that ask us to compute volume. So we'll just start with this one. This time we're not asked about volume, but we're just given an integral and we're asked to evaluate it. Probably the easiest way to evaluate this, is to switch to polar coordinates. Now, I know I want to switch to polar coordinates because I know that I've got an x squared plus y squared here. I could replace that with an r squared. And also, I don't know how to integrate cosine of x squared plus y squared with respect to x as it stands right now. We don't have a basic rule for that. U substitution won't work. So switching to polar coordinates is probably the best way to go. Now remember how we do this. If we want to switch to polar coordinates, we need three things. First, we need to write or describe the region of integration in polar coordinates. And the easiest way to do that is to sketch the region and then use our sketch to infer the range of values for r and theta, or to find the bounds for r and theta. They may be functions. Okay, so the first thing we do is sketch the region. Okay, now remember how this works. Oops, this should be dy dx. There we go. So these innermost bounds are bounds for y. So y goes from 0 to the positive square root of 1 minus x squared. The other way I would have had x going from this to this function of x, and that's not what we want. Y goes from a function of x to a function of x, and x goes from this constant to that constant. Now to sketch that, pretty much want to sketch four curves. You've got x equals -1, that's a vertical line. X equals +1, that's a different vertical line. Y equals 0, which happens to be the x-axis. And then you have y equals the square root. Every time I see y equals a constant minus a squared function, I think of circles. So it's probably a circle. Notice that y is the positive square root, so y has to be greater than or equal to 0. Let's square both sides. And then add x squared to both sides. So we have x squared plus y squared equals 1. That's a circle of radius 1 centered at the origin. But we only want the part of the circle where y is greater than or equal to 0. So we want the top half of the circle. So we're here. It's supposed to be a circle. It kind of looks like a parabola, but it's supposed to be a semicircle. Okay, so this is our region. Now that is really nicely, easily described in polar coordinates. So we sketch our region R, we see that it's part of a circle, that's great. So now we want to describe the region in polar coordinates. And when I say describe a region in polar coordinates, basically what I'm asking you for are bounds. I need bounds for R and bounds for theta. Now remember R, the value of R gives us circles radiating out from the origin. So r equals 0 is right here, r equals 1 is here, r equals 1/2 is here, r equals 1/4 is there. As r goes out from 0 to 1, we get the circle of radius 1, that disk of radius 1. Now we don't get the whole circle, we just get part of the circle. The fact that we get the top half only can be described by our values for theta. Theta starts over here and ends over here. So theta goes from 0 to pi. Oh, isn't that nice? Wouldn't you rather integrate from 0 to 1 and 0 to pi as opposed to there to there and there to there? And not to mention the fact that cosine of x squared plus y squared is difficult to integrate with respect to y or x. We don't have any rules for that. Okay, so we've got new bounds in terms of r and theta there. Now we also need a new integrand. So you need to find f of x, y in terms of r and theta. And our f of x, y, that's cosine of x squared plus y squared. I replace x squared plus y squared with r squared, and I get that. And then the last thing we do is we replace dA, which is dy dx in this case, with whatever it is in terms of r and theta. So it's r dr d theta or d theta dr, whichever one we prefer. And it doesn't really matter because the bounds for r and theta are both constant. So we can integrate with respect to whichever one we want first. So we've got the double integral over r of f of x, y, dA can be written this way. So after we've set everything up, we've come up with everything that we need to write the integral in terms of r and theta, then we actually do it. We write the integral in terms of r and theta and evaluate it. So I will integrate with respect to theta last. So we'll have the integral from 0 to pi of the integral from 0 to 1 of f of x, y, which is cosine of r squared. And dA is r, which I'll put out front, times dr times d theta. Now that I've got this double integral, I will evaluate the integral. So do the inside integral first. And notice you've got an r squared here and an r here. It's not a basic rule because it's a product, but a u sub will work. The derivative of r squared has an r in it, so u sub will work. So let's let u equal r squared. Then du is 2r dr. Multiply both sides by 1/2. And then we need new bounds. When r equals 0, u equals 0 squared, which is 0. When r equals 1, u equals 1 squared, which is 1. It's very coincidental that the bounds for u and r happen to be the same, but they are this time. So r dr can be replaced by 1/2 du. And then this that's left over, that's cosine of u. So that's my u, and this part is 1/2 du. The antiderivative of cosine is sine. Replace u with 0, replace u with 1, and subtract. So you'll get 1/2 sine of 1 minus 1/2 sine of 0, but sine of 0 is 0. And that's all constant, so I can factor it out and multiply by the integral from 0 to pi of 1 times d theta. So we just get 1/2 sine of 1, that's our constant. Antiderivative of 1 with respect to theta is just theta. Evaluate from 0 to pi. And so we get, when theta equals 0, or when theta equals pi, we get pi. So we get 1/2 times sine of 1 times pi, or pi over 2 times sine of 1 minus 0. So the value of the integral is pi over 2 times sine of 1. It's actually pretty simple. We sketch the region, we describe it in polar coordinates, find your new integrand, replace a dA with r dr d theta. Substitute, and then evaluate the integral, do the innermost integral first, and then work your way out. Okay, so that was our first example. Here's another one. This time we're asked to find the volume of a region. Whoops, trying to get my camera right. There we go. We want the volume of a region between z equals 0, that's the xy plane, and z equals natural log of x squared plus y squared. Over the region R, where the R is a set of xy pairs, such that x squared plus y squared is between 1 and 4. Well, remember what x squared plus y squared is. X squared plus y squared is r squared. So if we're saying that x squared plus y squared is between 1 and 4, what we're really saying is r squared is between 1 and 4. So just like before, we are going to start by graphing the region R. And then we'll describe R in polar coordinates. Now if r squared is between 1 and 4, that means r is between 1 and 2. So we've got a circle of radius 1 and a circle of radius 2. And r is this entire ring. So I think we've got our bounds. R ranges from 0 to 2. And if we start over here and we go all the way around, theta has to go from 0 to 2 pi. Okay, so those are our bounds. We've described R in polar coordinates. Now we're asked to find the volume of the region between z equals 0 and z equals natural log of x squared plus y squared. Now, when x squared plus y squared equals 1, so we're on this circle, z is natural log of 1, which is 0. But as x squared plus y squared increases from 1, so it goes from 1 to 4, well then, the natural log of a number between 1 and 4, not including 1, is positive. So this is above the xy plane. I don't know exactly what it looks like, but I know on the circle of radius 1, z is 0. So we're right there. And on a circle of radius 4, circle of radius 2, it's not a great picture, sorry. Z is natural log of 4, whatever natural log of 4 is. And I don't know exactly what that is. But it's going to take on some values over here on a circle of radius 2. It's supposed to be raised up. That's a really bad one. But I think what we're going to see is a surface that looks kind of like this. So it's extending, we're looking at the volume underneath this surface, and that surface is given by z equals natural log of x squared plus y squared. It's the volume between this ring in the xy plane and this surface up here. And that it's supposed to be a circle of radius 2 with z equal to natural log of 4 right there. It's not a great picture, but I think with this picture that's enough to help us to write down the integral for the volume. The volume of the region, well, it's just the volume between this and the xy plane, so it's going to be the double integral over r of the function, which happens to be natural log of x squared plus y squared, and we'll integrate over r, so we have a dA over there. Well, in order to evaluate this, we need to describe the region R. Here we've described it in polar coordinates. Now, if I want to evaluate this in polar coordinates, I need an integrand in polar coordinates, and I need dA in polar coordinates. So we had an intermediate step here. We set up the integral representing volume. And now we're going to write that integral in terms of r and theta by describing our region R, which we already have in polar coordinates, and now we need a new integrand. Find the new integrand. It's actually pretty easy. F of xy is natural log of x squared plus y squared, and in polar coordinates, x squared plus y squared is r squared. Now, because of our exponent properties, or not exponent properties, our log properties from algebra, I can actually bring that 2 out front. So that's actually 2 natural log of r, which is nice. I'm not sure. Maybe we want it that way. We'll see in a little bit. So we can either write the integrand as natural log of r squared, or we can write it as 2 natural log of r. Either way would work. Okay, so we've got a new integrand, and we need a new dA. dA is now, of course, r dr d theta, because that's how we convert dx dy and dy dx to polar coordinates. So now you put all those pieces together, and you write your integral in terms of r and theta. So we have volume equals the double integral over the region R. And R can be described this way. Little r goes from 1 to 2, and theta goes from 0 to 2 pi. And then we need our integrand. Our integrand can either be written as natural log of r squared or 2 natural log of r. I think I want to write it as 2 natural log of r. And then dA, this dA over here, can be replaced by r dr d theta. So I'll put my r there. There's r dr d theta. Now here I can use integration by parts to evaluate this. If I used this, natural log of r squared, well, that would work too. I would do a u sub first because I'd have natural log of r squared and an r out front, but then I'd have to use integration by parts to evaluate that. So you have to use integration by parts either way, so I'll just use integration by parts for this one. So now that it's all set up, I've got new bounds, a new integrand. I replaced dA with r dr d theta, and we just evaluate. Start in the innermost integral first. So we anti-differentiate with respect to r, and the way we do this is we assign part of this to be u and everything else to be dv. Now, if there's a natural log in your integrand, that's your u. dv is everything else. Then we anti-differentiate 2r to get v, get r squared. Differentiate u to get du. Don't forget your dr. And then according to integration by parts, the result is u times v, so we get r squared, natural log of r, minus the integral of v times du. And all of this is evaluated from r equals 1 to r equals 2. Now don't integrate this separately. A lot of people want to call that 1/3 r cubed times the natural log of the absolute value of r. Don't do that. We don't have a product rule for antiderivatives. You have to simplify this first. This r cancels with one of those r's, so you just end up with a single r. The antiderivative of r, we add 1 to the exponent and divide by the new exponent. Then plug in r equals 1, plug in r equals 2, and subtract. When r equals 2, we get 2 squared is 4, natural log of 2, minus 4 times 1/2, which is 2. And then when we substitute in r equals 1, natural log of 1 is 0. So we get 0 minus 1/2 times 1 squared. d theta. Now all of that is a constant, so we end up with 4 natural log of 2 minus 2 plus 1/2, so that's minus 1.5 or minus 3/2, or you could say 1.5 if you want to. That's all constant, so I'm factoring it out. The antiderivative of that constant with respect to theta is that constant times theta. Replace theta with 0 and 2 pi and subtract, and we get this. When I evaluate this at 2 pi, I get 4 natural log of 2 minus 3 over 2 times 2 pi. So I'll distribute my 2 pi, and I'll get that. And at 0, we would get 0, and we subtract 0, so that doesn't change anything. Okay, so we found the volume of this region by identifying the bottom function and top function. We figured out it turned out to be a single function, and we had to turned out to be a single function. We're integrating under this, we're integrating this function over this region R. And then it turned out, because this integral was easiest described in polar coordinates, we could evaluate it in polar coordinates. And we also knew that that was coming because the region R was easiest to describe in polar coordinates. We had this sort of donut shape, this washer shape. So we described R in polar coordinates. We found the integrand in polar coordinates. We actually had 2 different versions to choose from. And then we replaced dA with r dr d theta. And then when you substitute in your new bounds, your new integrand, your new dA, that's your r dr d theta, then you just evaluate the integral. And it turned out to require integration by parts, and then there were no thetas. So we just ended up with a constant times theta. And we replace theta with 0 and 2 pi, and we get this answer. Okay, so we're going to do one last one. Now in this example, we're asked to find the volume inside a hemisphere. So they're telling us in advance it's a hemisphere, given by z equals this positive square root, and we want the volume inside the hemisphere and inside the cylinder given by this. Now, this looks like the equation of a circle, and it is, but it's a circle in the xy plane. Z is free to be anything. So this is just a right cylinder. It goes up and down. It's parallel to the z-axis, and that cylinder is going to intersect our hemisphere at some points. So let's draw the hemisphere and then draw the circle in the xy plane and imagine extending it to find out what that volume looks like. So, okay, they told us this was a hemisphere. Now, if you don't believe that person, you can rewrite this so that it looks more like a sphere by squaring both sides. Remember that if z is the positive square root, z has to be greater than or equal to 0. That's why it's a hemisphere. It's not the whole sphere. Then add the x squared and y squared to both sides. And you see, we've got a sphere centered at the origin. R squared is 16. So the radius of that sphere is the square root of 16. So r equals 4. So as soon as I see this problem, I just started doing it without describing it to you. I'm sorry about that. The first thing I want to do is sketch this. So we want to sketch the volume if we can, as best we can. And then, of course, once you have that volume, you also want to sketch the region R and describe it. Okay. So I realize this is a hemisphere, they told us. So I wrote it in the form of a hemisphere so that I could recognize it. I see my center is 0, 0, 0, and the radius, and it's 0, 0, 0 because I'm not subtracting anything from the x, the y, or the z, and the radius is 4. So this is a sphere of radius 4 centered at the origin. This doesn't have to be perfect. We just do the best we can. Okay. So that is what we're looking at. We're looking at the top half of a sphere of radius 4. Now the region R is defined by this cylinder. We've got x squared plus y squared minus 4x equals 0. Now that's a circle in the xy plane, but then it's going to extend up because there's no z in it. Z is free to be anything. So it's a cylinder. To find out which cylinder it is, I need to rewrite this. I need to write it differently, which requires completing the square. So I've got x squared plus y squared minus 4x equals 0. Now to complete the square, I need to write my x's together and my y's together. If there is a coefficient of 1 in front of the x squared, and there is, the number in front of the x is b. If there was a different number in front of the x, I'd have to factor in front of the x squared, I'd have to factor that out from both terms, but this time I don't have to. b is -4. Take half of that and square it. -2 times -2 is +4. That's what you add to complete this square. If you're going to add that to this side, you have to add it to the other side as well. So this gives us an x minus 2 quantity squared plus y squared equals, simplify the right-hand side, you get 4. Now comparing this to the standard form of the equation of a circle, since I'm subtracting a 2 from the x coordinate of my center is 2. Since I'm not subtracting anything from my y, the y coordinate of my center is 0. So this is centered at x equals 2, y equals 0. And the radius squared, that's the right-hand side, that's 4. So we take the square root. R is 2. So we're centered right here. We're going to add 2 and subtract 2. So you're going left 2 and right 2. And then you're going to go up 2 and down 2. Now that just looks like a circle, but remember, z is free to be anything. So even though it doesn't look like it, I'm try to draw my circle, my cylinder. That is our cylinder right there. Trying to draw it. There's your cylinder. That's what it looks like. Z is free to be anything, so it looks like this. See it? See our circle down there? Okay, so I've got a sphere, or excuse me, a cylinder. It's centered at x equals 2, y equals 0. So that looks like this. And we go back 2 in the y direction and forward 2 in the y direction. So the cylinder, the base of the cylinder is right here, but we're taking that cylinder and it's intersecting this hemisphere. So what you're going to see is like part of this sphere is cut out. It's a little bit hard to draw. That volume is what we're looking for. We want the volume of that. So we wanted the volume inside the hemisphere and inside that cylinder. And it turns out it's just going to be a regular volume integral because it's the volume under the hemisphere between the xy plane and the hemisphere. It just so happens that the region of integration R is this offset circle, this circle that's not centered at the origin, but it's centered at x equals 2, y equals 0. So this is our region R. Okay, so we've sketched the volume, we sketched the region R, and we know that the volume because we need to set up the volume integral. We know that the volume is the double integral over r of the function times dA, and the function is the square root of 16 minus x squared minus y squared. And I see that x squared plus y squared, if I factor out that -1, this is an excellent candidate for polar coordinates. So we need three things. We need r in polar coordinates, we need an integrand in polar coordinates, and we need dA in polar coordinates. We'll substitute those and then we'll evaluate the integral. Okay, so I need to describe this in polar coordinates. Now, this is easiest to describe in polar coordinates by starting with the original equation. We had to complete the square so that we could graph it, so we knew what it looked like. But this is probably easier to convert to polar coordinates than this. In fact, if I was given this, I would probably square this to get this. I'd subtract 4 from both sides and I would get this, and then I would write that in polar coordinates. So we're just going to skip that step. We're going to go right here and write that in polar coordinates. So this is the equation of the circle. So this is the boundary. X squared plus y squared can be replaced by r squared, and then we're subtracting 4 times x, and x is r cosine of theta in polar coordinates. So you're just substituting, and then add the 4r cosine of theta to the other side, to both sides. And then you can divide out the r. Normally we don't do that because we don't want to accidentally divide by 0. But we see that r is equal to 0 at lots of different values of theta. At theta equals pi over 2, we get cosine of pi over 2 is 0, so we would be right here. Okay. And 3 pi over 2, and lots of different values of pi over, or lots of multiples of pi over 2. We'll get r equals 0. Okay, so now we want to describe this region in polar coordinates, and there are lots of different intervals of theta values that will give you this. Actually, let's start with r. So r goes from here out to here, so we're going to think of r as starting at 0 and going out to 4 cosine of theta. And now let's talk about theta. There are lots of different values of theta that will trace out this circle. I still like to think of it as an angle that sweeps, though. It helps my intuition. So theta is starting over here and ending over here. This circle is tangent to the y-axis. With that in mind, I see that one set of bounds that I can use for theta is theta starting over here, because I want to go counterclockwise, which I would say I'll represent that by negative pi over 2. It's starting over here and then ending over there. So if I go from negative pi over 2 to positive pi over 2, I get the whole circle. Okay, so I've got new bounds. What else do we need? We need a new integrand and a new dA. So I've got bounds. R goes from here to here. From our picture, we've decided that theta goes from negative pi over 2 to pi over 2. And you could use 3 pi over 2 to 5 pi over 2. That's fine. Just make sure it goes through pi radians, and then theta goes in the positive direction to get the right value for your integral. And now we need the integrand, a new integrand. So f was a function of x and y, and it was given by this 16 minus x squared minus y squared. Now if I factor out the negative from both of those terms, negative 1 times x squared gives me my first term, and a negative 1 times a positive y squared gives me my second term. So I can replace this x squared plus y squared with r squared now, and I just get that. And then we need a new dA. dA will be replaced by dr, or r dr d theta. So our volume integral becomes the double integral over r of this and now I can replace my bounds with these bounds. Theta goes from negative pi over 2 to pi over 2. R goes from 0 to 4 cosine of theta. Our new integrand in terms of r and theta is the square root of 16 minus r squared, and dA is r times dr d theta. Now we evaluate the innermost integral first and go on from there. But let's write out our steps first before we do that. We set up the volume integral. We got new bounds. Then we got a new integrand. And then we found the new dA, or just identify or state the new dA. Then we write our integral in terms of r and theta. And then you just evaluate it. Start from the innermost integral first. So we're here. Now I've got a product, so I don't have a basic rule for that, but I can do a U sub. Notice that the derivative of this inside function is a negative 2r, and I'm not worried about the negative 2. I'm worried about the r. The derivative of this is negative 2r, and there's an r right there, so U sub's going to work. So let U equal the inside function under the radical. du is negative 2r dr. I don't really want that negative 2, so I will divide both sides by negative 2. So now I'm ready to write all of this in terms of U, but I need new bounds. When r is 4 cosine of theta, U is 16 minus r, which is 4 cosine of theta squared. So square the 4, square the cosine. We get that. If you factor out the 16, you have 16 times the quantity 1 minus cosine squared, and that simplifies because 1 equals sine squared plus cosine squared. By our Pythagorean identities, U is equal to 16 sine squared theta. That's our new upper bound. And when r is 0, we get 16 minus 0 squared, so we just get 16. Okay, so we evaluate by using a U substitution. So you choose U, compute du, find new bounds for U, a new upper bound and a new lower bound. And now we'll evaluate the integral. Okay, so this is the square root of U. And r dr turns out to be negative 1/2 du. And then we'll have the integral from the new lower bound, which is 16, to the new upper bound, which is 16 times sine squared theta. And that's our innermost integral. It's d theta. Okay, now you can factor out the negative 1/2 if you want to. And we still have the 16 and 16 sine squared theta. Instead of writing that as a square root of U, I'll write that as a U to the 1/2 power, so I can use the power rule to anti-differentiate it. Start on the inside. We're going to work our way out. Okay, so now I've got negative 1/2, and the antiderivative of u to the 1/2 is u to the 3/2. We're adding 1 to the exponent, and then dividing by the new exponent. Dividing by 3/2 is multiplying by 2/3. Evaluate from 16 to 16 sine squared theta. 2/3 times the negative 1/2 is the 2's reduced, so you have negative 1/3 out front. And then over here, we have u to the 3/2. So that's 16 sine squared theta raised to the 3/2 minus 16 raised to the 3/2. Now you have to be very careful here. Very, very careful. And you're saying to yourself, why? Why do I have to be careful? Well, this is the square root of something cubed. Now we have a bad habit in math of sometimes simplifying things that only simplify in very special cases. Let's see. Well, I'll get back to that in a second. Let's simplify this first. 16 to the 3/2 can be written this way. That 2 in the denominator is the index of the root. So I can take the square root of 16 and cube it. That's one way to do this. So square root of 16 is 4. 4 cubed is 64. So we're subtracting 64 there. Okay. Now over here, what we've got is the square root of 16 sine of theta, or 16 sine squared theta, but then we're cubing it. Now watch this. You have to be very careful about this, because this square root is only going to produce positive answers. I know, you might want to just say that that's 4 sine of theta, but it's not quite 4 sine of theta. Careful. Watch this. It's 4 times the absolute value of sine of theta, and then we're going to cube that. And you might be saying, oh, Ms. Townsend, I never would have thought of that. I know. As a student, I never would have thought of that either. But let's think about why that's true. We have this habit in math class of saying, well, the square root of x squared is just x. And that's usually true. The square root and the squaring function undo each other, but only in certain cases. This only works when x is greater than or equal to 0. So when you're in algebra class and you're simplifying expressions like this, they usually say, assume all the variables are positive, and then you get to do this. But if the variables aren't positive, what you get is x when x is positive and negative x when x is negative. You're saying, I thought it was always positive. Well, it is. Let me show you. If I take negative 2 and I square it, I get 4. When I take the square root of 4, I get 2 back. So whatever this is that I started with, I always get the same number back but positive. So actually, like, this is true as long as I have this restriction. But if I don't want to write that restriction, I have to put an absolute value around that x. Because if that x happened to be negative and I square it and I take the square root, I'm not going to get negative 2 back. I'm going to get the same number but positive. I'm going to get the absolute value back. And sine happens to be negative a little bit on this interval from negative pi over 2 to pi over 2. Sine looks like this. Sine is negative over here. So I have to be careful. I might end up with something like a 0 volume when I don't get a 0 volume, because the square root of this is going to give me the absolute value of that. Okay, if you're not really sure about that, and most students are like, what? Wait, what? Come talk to me or text me and we can talk about it. Maybe we can talk about it during virtual office hours this week. It's just a little fine detail. It's a very important fine detail that will prevent you from getting the right answer. It'll prevent you from getting the correct volume. If you don't keep in mind that this square root of something squared just gives you that number as long as it's positive. If it's not positive, if it's sometimes negative, it gives you the absolute value of that number. Okay, so now we're going to cube this. And so we get 64 times sine of theta, absolute value of sine of theta cubed minus 64, and we're integrating with respect to theta. Okay, now we can split this into two pieces. Let's say on this interval from negative pi over 2 to 0, sine is a negative number. So on that interval, negative pi over 2 to 0. So on the interval from negative pi over 2 to 0, the absolute value of sine of theta is negative sine of theta. Because I'm taking negative numbers and then I'm multiplying them by -1 to make them positive. Absolute value of sine of theta is going to look like this. So I'll multiply those numbers by -1 to make them positive, and then we'll cube that. And yeah, we'll evaluate that integral. That's the first part. And then we have to add this integral, or the rest of this integral. This is the part from negative pi over 2 to 0. Now we need the part from 0 to pi over 2, the rest of it. On that interval, sine of theta is positive, so that just ends up being a sine cubed theta. I know this is a little tricky. We can handle it though. It's good for us. So factor out a -1/3, and we've got this integral now. That negative cubed is going to give us a -1 times that 64. And you can actually factor out a -1 there and there. It's going to make that positive. And then we'll have minus this. Okay. Keep going. Almost done. Okay, now the integral of the 64 sine cubed, I need to write that differently. Since sine is raised to an odd power, I've got to use my trig integrals, those identities. So I'll factor out the, let's factor out 64 from everything. And sine cubed, I want to write as sine squared theta times sine of theta. And then, so that's that first part, and then we'll also have an integral from negative pi over 2 to 0 of 1 with respect to theta. Now this can be evaluated by using a trigonometric substitution. Since sine was raised to an odd power, we save one sign for du and we let u equal cosine of theta. And since sine squared plus cosine squared equals 1, sine squared is 1 minus cosine squared. So that's really 1 minus u squared. And du, if u equals cosine of theta, is negative sine of theta d theta. And I've got a sine of theta d theta right there, so negative du is sine of theta d theta. Okay, so that's that part. And there's another integral we've got to evaluate as well, and we'll do that in a little bit. So let's just do this piece. We've got 64 over 3, and then we've got times this. At pi over 2, cosine of negative pi over 2 is 0. Then cosine of 0 is 1. And this will be 1 minus u squared times a negative 1. So that's u squared minus 1, because we can just change the order. Du. And then the integral of 1 with respect to theta is theta, and you evaluate from pi over 2 to 0 and subtract. Plus that other integral, which we'll evaluate in a little bit. So we've got 64 over 3 times the antiderivative of this. Add 1 to the exponent, divide by the new exponent. Subtract your variable, evaluate that from 0 to 1. Over here, substitute in 0, substitute in negative pi over 2. So we're subtracting a negative, that'll make it positive. So we get that. Plus the second integral. So now you've got 1 1/3 minus 1 plus pi over 2 plus the second integral. So we end up with 64 over 3 times negative 2/3 plus pi over 2 plus the second integral. Okay, gotta keep going. Second integral. The second integral was, factor out a 64 on that as well. 64 over 3. Want to show you that integral again. We're here. It's that one. Times the integral from 0 to pi over 2 of sine cubed theta minus 1. And this is pretty much the same integral that we just did. So after doing your U sub, well, actually we probably shouldn't do that. Let's show all of our work. Replace sine of theta, or sine cubed theta, with sine squared times sine. Okay. Sine squared is 1 minus cosine squared. Whenever you're doing a trig sub where sine is raised to an odd power, let u equal cosine. So we get 1 minus u squared there, where u is cosine of theta. Du is negative sine of theta d theta. So negative du is sine of theta d theta. That's that right here. That right there. Okay. Now we need new bounds. When theta equals pi over 2, cosine equals 0. When theta equals 0, cosine equals 1. So what do we get? We've got 64 over 3 times all of this. I'm just copying it again. 64 over 3 times this integral. When theta equals pi over 2, we get 0. When theta equals 0, plug that in, cosine of 0 is 1. The negative times that's just going to change the orders. That makes that u squared minus 1. Integrate it with respect to u. The antiderivative of negative 1 with respect to theta is negative theta, and we'll evaluate from 0 to pi over 2. Okay. Not too bad at all. Antiderivative of u squared is just 1/3 u cubed. Antiderivative of 1 with respect to u is just u. Substitute in 0 and 1 and subtract. Over here we're going to substitute in pi over 2 and 0 and subtract, so we just get a negative pi over 2 minus a negative 0, which is just plus 0. At 0, you get 0. At 1, you have 1/3 minus 1. So now I've got a negative 2/3 here times a negative 1 is a positive 2/3 minus pi over 2. No, what happened? Something happened. I must have made a mistake somewhere. Man, you see it? That's going to cancel with that. That's going to cancel with that. And we get 0 for our volume. I'm sure that the volume is not 0. I'm sure the volume is supposed to be this plus that, but I must have made a sign error somewhere. 0 volume. Ah! Volume can't be 0. It's not 0. So all that work just to find out that I made a sign error somewhere. Not really sure where it happened, but I thought that taking care of that absolute value would have helped, but I thought that was going to fix the problem. Oh, actually, I think this is supposed to be negative. Ha ha ha! I figured it out. This is supposed to be negative, that's supposed to be negative, that's supposed to be negative, that's supposed to be negative, and we don't get this, thank goodness. We get 64 over 3, and we're going to end up with pi over 2 plus pi over 2 is pi, and a negative 2/3 minus 2/3 is going to be negative 4/3. And that is the volume, because I missed that negative sign from earlier. I'm glad. All that work wasn't wasted. That's the right thing. Sorry about that. Hate when I make a little sign error. Don't you hate when that happens to you?